Thanks for the invitation. Okay, so the natural starting point is the following theorem explained by Kieran in October, I think, of the theorem of Beauville and Voisin in 2004. For the Chow rings of K3 surfaces. So let S be a projective K3. Then there exists a well-defined zero cycle of S of degree 1 such that, firstly, for any two divisors dd prime in S, then the intersection product in Chow ring is proportional to this specific class. So it's the intersection number times this class in the Chow group of zero cycles. And secondly, the second Chen class of this K3 surface is also a multiple. It's of degree 24, so it's 24 times this class in Chow 0. So this is a statement of theorem. This theorem is surprising, as point out in that paper, because by Mumford's result, when S is K3 surfaces, so have geometric genius positive, this CH0 of S should be infinite dimensional or very large. But however, any intersection product of two divisors is also proportional to that, and the second Chen class is also a multiple of it. So it's kind of surprising. And as Kieran has explained this, I should mention that the proof uses the result of Bogomolov-Mumford, saying that for every ample linear system, there is always a chain of rational curves in it. Now, what is relevant to this talk is the following insight of Beauville's insight in his paper of splitting principle in 2007, saying that we should view this, at least the first part in the theorem, as a phenomenon of multiplicative splitting of Bloch-Beilinson type. Multiplicative splitting of the Chow ring of S of Bloch-Beilinson type. Now I need to explain what is multiplicative splitting of the Chow ring and what do I mean by Bloch-Beilinson type. So let me start the definition here. Definition. So let X be a smooth projective variety, complex variety over C. Then we say that the Chow ring of X, so from now on I will work over with rational coefficients. Chow ring of X admits a multiplicative splitting if, so first of all, it's a splitting direct sum decomposition. So CHI for any I, it's a direct sum of J in Z, but it's a finite sum such that it's CHI, X, and J, such that this is multiplicative, which means if we have two cycles, first in ij, another in I prime, j prime, j prime, then the intersection product should live in, of course, it's a cycle of codimension I plus I prime, but it should live in the direct factor of j plus j prime. That's very simple. It's just a multiplicative splitting. But what is interesting is that if, so I continue the definition, we say that it is of Bloch-Beilinson type if, so the following holds. So 3, for example, chi of x of j is 0 for j negative, and for the cycle class map from chi x, the 0 part goes to, so the cycle class map goes to 2i of x, the Betti cohomology with Q coefficient. This is injective, Of course, I can come up with more conditions. For example, like finiteness condition, like fi xj is 0 for j larger than I, or even like, I mean a lot of like the algebraic Jacobi map of chi x of 1 goes to the intermediate Jacobian 2i minus 1 of x is injective, etc. But it's just too strong. Okay. There are a lot of conditions that I can put.
Don't you want all the pieces strictly positive? That would be the curve. It's a bit more.
Yes, yes. So
Don't you want something?
So when I say multiplicative splitting, it's just something like naively, but
Don't you want actually the kernel of the cycle map, class cycle map should be the sum of those? No?
Oh yes. So you mean this? Oh yeah, the cycle class map restrict to the chi x with positive degree is 0, right? Yeah, sure. So that makes sense to say it's injective. Thank you. Now I should say that the existence of such splitting is very restrictive. However, the filtration associated to that, the filtration associated to it, that means if I define fj of chi of x with rational numbers to be these pieces with so it's s bigger than j of chi of s. That's a filtration, and this filtration is expected, is conjecturally expected to exist functorially for any smooth projective complex varieties. Any smooth projective varieties over C with all the reformulations of 1, 2, 3, 4, 5, 6. For example, 1 is just it has the filtration, and 2 says that the fj is multiplicative, and 3 says that it's it starts with f0, And 4 says that it's the F1 part is the homologically trivial part, etc., etc. It is called Bloch-Beilinson filtration. But this conjecture is out of reach for the time being. No, because it's multiplicative. So the point is that this is the really, really strong condition. Multiplicativity. It's not true. So I will explain it in a minute. So now let us revisit Beauville-Voisin theorem. Revisit of Beauville-Voisin theorem. So let me decompose the Chow ring of a K3 surface. So as a K3 surface, projective, as follows. So CH0, CH0 of S is just one-dimensional. So so it's just I don't know. It's just CH0. It's Z times the fundamental class of S. So it's J equals to 1, J equals to 2, 0, 1, 2. So it's 0, 0, 0. And the CH1 of S. So S is simply connected, so there is no pick 0. So everything is in CH1 of S, 0, and plus 0 here. So the non-trivial part is the 0 cycle of the K3 surface. I will decompose it as this specific class, CS, plus there is no Albanese for this K3 surface, so I put just 0 here, and here just the Albanese kernel. Or in other words, these cycles, 0 cycles of degree 0. Now, if you look at Beauville-Voisin theorem, it says that this is a multiplicative splitting of Bloch-Beilinson type. So the only non-trivial part here, because for a surface, the Bloch-Beilinson filtration is well known. It's just given by the filtration here. And so the only non-trivial part is the multiplicativity here. And it says that every two divisors, the intersection lands into a multiple of this specific class. Or rather, the theorem, the one part. Let's forget about the second for the moment. Now, let me say another example of this multiplicative decomposition. I will put it here and keep it in for later use. So yet another example. This is example of Abelian varieties. So let's say it's the theorem of Beauville. Let's say A, B, an Abelian variety of dimension G, a complex Abelian variety. Then we have a multiplicative decomposition. So the CHI of A with rational coefficients is decomposed as J from I minus the dimension goes to I think. So it's just CHI of A to J, where now we have a very good description of this summons. CHI A J is this cycle with rational coefficient such that the multiplication by M map, M on the bar, pull back alpha, acts as M to the power of 2I minus J times alpha. Sorry for the weird index, but it's kind of traditional thing. So for any M in Z, and this M bar is the multiplication by M map for Abelian variety. So it says that this CHIJ part of this Chow group behaves like the cohomology of degree 2I minus J. So when J is 0, it behaves like the cohomology of 2I. degree 2I. The fact that this is a direct sum decomposition is kind of trivial, and the multiplicativity is also trivial because if we have ij intersect with I prime j prime, because the intersection it's eigenspace decomposition, so the degree adds, so it's trivial. But the non-trivial part is that it is expected to be the Bloch-Beilinson type. So the conjecture of Beauville is that this is of Bloch-Beilinson type. More concretely, it says the following. So I will use the same number, so maybe 3. It says that CHI of A of J is 0 for any J, for any J negative, and also the cycle class map from CHI A 0 goes to the cohomology of 2I of degree 2I is injective. And here, of course, the other parts is when we apply the cycle class map, it vanishes by this description. So now we have two series of examples of multiplicative decomposition of Bloch-Beilinson type, well, at least conjecturally. Now we ask the following question. No, not me, I mean Beauville. Ask the following question. So what kind of, what class of varieties can we expect this? Such splitting. Of course, a natural class that contains K3 surfaces and abelian varieties would be the class of all smooth projective varieties with trivial canonical bundle. But this turns out not to be true. So, but the observation, there is some examples that for some strict Kähler-Vial varieties, it's not true. Not true in general. So now the natural question here, still by Beauville, is that, is it true for some natural generalizations of K3 surface, namely for Hyperkähler varieties? As we know, the class of Hyperkähler varieties behave sometimes very like Abelian varieties, so it's kind of natural to expect that. So let me recall you this definition of Hyperkähler varieties. Now let X be still a smooth projective. C. We say X is Hyperkähler. I will note HK if, so firstly it's simply connected. And then it's uniquely symplectic. So the holomorphic 2 form is one-dimensional and then generated by some non-zero element eta, which eta is non-zero. Sorry, eta is some symplectic holomorphic 2 form. Here, symplectic means eta is non-degenerate at each point of X. So this is the definition of Hyperkähler variety. Okay. let me give you some examples of Hyperkähler varieties that is that's relevant to our discussion. Just put them here. Some examples. There are two series of examples constructed by Beauville. Where S is a projective K3 surface, then we can look at S bracket n. By definition, it's the Hilbert scheme of length n subschemes of K3 surface. This is Hyperkähler of dimension 2n. And the second example is also given by Beauville. If we start with Abelian surface, and we look at the same thing, the Hilbert scheme of this Abelian surface, we can have the Hilbert-Chow morphism go to the symmetric product of this Abelian surface, and we can go further because A is Abelian variety. We can have the group law here, so we can go to this Abelian variety by summing up all the supports. Then it's easy to see that this is an isotrivial fibration, and we take any fiber of it. So we can define Kn of A is just any fiber of it. So let's say this morphism is sum as inverse of for example, taking the fiber over origin. This is called the generalized Kummer varieties. Generalized Kummers. Because it's generalization of Kummer K3 surfaces. For example, K equal to 1, it's just the desingularization of A quotient by this -1 involution. So it's K3 surface. Now, there is also the beautiful example of Beauville-Voisin given by any Fano variety of lines, Fano variety of lines of cubic fourfolds, etc. There are also some example given by O'Grady for some resolution of singularities, of some moduli of sheaves on K3s, etc. And also deformations of all these examples are Hyperkählers. Now, I can state the conjecture of Beauville. Which says that, so the conjecture A, it's called Beauville's strong splitting principle. Strong splitting principle says that for any x Hyperkähler, projective Hyperkähler, then the Chow ring of X admits a multiplicative splitting of Bloch-Beilinson type. But this, as I said, this is very strong, and it uses some Bloch-Beilinson things. And we want some down-to-earth version of this conjecture. Now here is the Beauville's weak splitting principle, and there is no splitting at all in the statement. So still let X be projective Hyperkähler. Now we look at the subalgebra, projective Hyperkähler. We look at the subalgebra generated by divisors of X. This is sub Q algebra of the Chow ring of X with Q coefficients generated by divisors. Then we look at the restriction of the cycle class map to the subalgebra. The conjecture says that this is injective. Yes. Now let me explain why conjecture A implies conjecture B. This is kind of easy here. So conjecture A will imply conjecture B. It's very easy because so we know Hyperkähler varieties are all simply connected. So CH1 is everything lives in 0 here because this is just divisors, and therefore the algebra generated by this guy, this algebra, and by the multiplicativity, we know that this lives in the subalgebra of the Chow ring of 0 here. And by the condition that I just erased, the cycle class map restricted to this subspace is supposed to be injective. So this is supposed to be injective here. Therefore, this is conjecturally injective. Now, if you remember that in the theorem of Beauville-Voisin, we have a second part, which says that the second Chen class of the tangent bundle is also some multiple of this CS, this specific class. Then we can the idea of Voisin is to incorporate also this Chen classes of a tangent bundle into the picture and state a stronger conjecture. So we can state a conjecture B plus. It's the so-called Beauville-Voisin conjecture. Which says the following. So X is still projective Hyperkähler. Then if we look at the subalgebra generated by divisors and all the Chen classes of the tangent bundle, then we look at the restriction of the cycle class map to the cohomology. And the conjecture says that this is injective. Now let me say some known cases of this conjecture. Some known cases. So for this is due to Voisin. For as a K3 surface, so how to say as a K3 surface, then this is okay for the Hilbert scheme of K3 surface with this n not too big, so it's some bound in terms of the transcendental Betti numbers of the K3 surface. So this is okay. And also by Voisin in the same paper, she proved that this is okay for Fano varieties of lines of cubic fourfolds. Of cubic fourfolds. And then I prove this. Sorry, I prove this for generalized Kumers. Then we have the example of in. Oh yeah, oh sure. So all these are for conjecture B plus. In prove this for any Hilbert scheme of K3 surfaces of finite dimension with as finite dimensional in the sense of Kimura. In the Kimura sense. And then, as far as I know, there is also a theorem of, so I think it's read. Yeah. For any Hyperkähler with an L in the line bound on it, which is 0 when we apply the Beauville-Voisin form. So let me say Hyperkähler. And X deformation equivalent to the K3 surface Hilbert N type or generalized Kummer type. Generalized Kummer. Then, but this is just for conjecture B. So there is no Chern classes of tangent boundary involved here. Now I want to explain the proof of this result here. Proof for generalized Kummers. So the first step is to use an idea of Voisin when she proved this K3 surface, Hilbert scheme of K3 surface type, to relate the cycles of Hilbert scheme of K3 surface to the cycles of product of K3 surfaces by using the theorem proved by Marc de Cataldo and Miolini. So this theorem is for any projective smooth surface, and any smooth projective surface. Then we can look for any mu a partition of n. We can look at the Hilbert-Chow map. From the Hilbert scheme, go to the symmetric product. Then we look at this some power of S here. Mu is of length L. So this is just numbers with some n. And we look at the morphism from S to the power of L to the symmetrical product given by just weighted sum. Then we take the fiber product, but with a reduced scheme structure. We take the fiber product with a reduced scheme structure. Let's call it E mu. It's some cycle lives in the product of a Hilbert scheme and a product of surface. And we will look at it as some correspondence between these two varieties. Then the theorem says the following. Says the sum of all over all partition with some coefficient. Now, if we look at the push forward by this correspondence, then we get an isomorphism of the Chow of Hilbert n go to the direct sum of the Chow of some product of symmetrical product of surfaces where S mu is just SA1 times SAN. Now we write mu as some standard way that there are A1 times 1, A2 times 2, etc. It's just the symmetrical product of all these pieces. Yeah. And the point that that will be relevant to us is with inverse. The inverse is given by also by essentially the same correspondence, but with different coefficients here. I will put m mu prime and m mu double prime here. So now you know that the Chow group of symmetrical product is just a direct factor of the Chow group of products. So in some sense, we have this. So in particular, the Chow ring, the Chow group of the Hilbert scheme gets injected into the direct sum of all mu of all the products. How to say this? Length of mu. So let me denote L be the length of mu. So to here, and the injection is also given by this cycle, and the projection is also by the transpose cycle. So this is just direct factor of all the cycles in all the products of surfaces. Now, the strategy of proof is very easy to explain. Now the sketch of proof. Now if we start with some alpha in the subalgebra generated by Kn of A and the Chen classes of the tangent bundle of Kn of A. Now we look at the same diagram for A. So we have E mu goes to A to the power of L for any mu of length L. We have the Hilbert scheme of the Abelian surface goes to symmetrical product. This is reduced guy. And we can look at a further composition of the map by this group law in the Abelian surface. Then now this map is just weighted sum that given by the same formula. But now this summation is regarded as something in the Abelian surface. Now we take the fiber, of this diagram over the origin. Over the origin here, we get a diagram I call this gamma mu from the kernel of this map, of this weighted sum map, to here. This is just our generalized Kumars. Well, I switched n from n minus 1, but it doesn't matter. So maybe I put n plus 1 here. Any mu a partition of n plus 1. So we get our generalized Kummer's by definition. And by De Gadardo and Miolini's result, we know that by De Gadardo and Miolini, we know that the summation of all mu to n, m mu prime, m mu double prime, e mu up star, e mu lower star is identity on the Chow group of the Hilbert scheme. Chow group of the Hilbert scheme. And by base change, we can have this similar result for generalized Kummer's. Now, given this alpha in this subalgebra, if the cohomological class of alpha is 0 in the cohomology of the generalized Kummer's, then we know that, of course, this correspondence applies to alpha. Applied to alpha, we get something cohomological trivial. So this is cohomological trivial in cohomology of this. So I should say that this kernel, I will call this B mu, which is a non-connected abelian varieties. It's just some abelian varieties, disjoint union of isomorphic abelian varieties. This is just trivial here. Now here comes the important lemma, which is down in the paper by Voisin when she proved the Hilbert scheme of K3 surface case. This is due to Voisin and based on the calculation given by adding the thread, Goethe and Lian, that this cycle alpha in this abelian variety is in is in the subalgebra generated by the symmetric line bundles on abelian varieties, B mu. So this is the symmetric line bundles, and this is just subalgebra generated by this. And yes, it's invariant under the involution. Now, why I keep this board? Because we can play the same game for abelian varieties. So we have, for abelian varieties, the line bundles can be decomposed into, so this is just Picard group, and decomposed into the pick 0 of A tensor with Q, which is just dual abelian varieties, plus the symmetric line bundles of A. And this part in our decomposition is just the CH1 0 part. And this is our CH1 1 part. So we know the splitting in the divisor case. And now we can look at the subalgebra generated by symmetric line bundles here. Of course, it will be contained in by multiplicativity in the subalgebra with subscript 0. And this is supposed to be injective into the cohomology of the abelian varieties. And by the same argument, we know that this is supposed to be injective. So the question of Voisin. So this is all conjectural. Question of Voisin is that can we prove this injectivity? So injectivity here. Here. Now, fortunately, we have this following theorem which answers affirmatively of this question. This is more or less independently due to Ancona, Moonen, and Peter O'Sullivan. That so the answer is yes. So this is injective. This morphism. Yeah. Oh, yeah. This is for any abelian variety. So yeah, I messed up with the notation A, but this A is for any abelian varieties of dimension G. So this morphism, when we restrict the cycle-class map to this subalgebra, this is injective. Now I can continue the proof. Where am I? Yes. So if we have this lemma that this cycle-class map is in this subalgebra, then we can upgrade any homological trivial cycle to conclude that this is actually 0 modulo rational equivalence. So we know that gamma mu star alpha is 0 in Chow of this abelian variety. And now we can conclude by this identity, right? So we know that mu and mu prime and mu double prime, gamma mu star, gamma mu lower star. Oh, yeah, maybe it's lower star. It doesn't matter. So this is 0 in Chow. So that ends the proof. Of course, there are some subtle things in the proof because this is non-connected abelian varieties, and we have always this cover problem. But anyway, the main idea is very clear here. So in the last 10 minutes, I want to say something work in progress here. Be what?
We have a map. They understand
Yeah.
situations where you have a map x to y between varieties that relates their respective sequences.
Oh, yeah, this is related, actually. This is related to Claire's work of vibration of K3 surfaces. But this is a very restrictive situation.
So, and you wouldn't expect the valence and filtration to split outside those cases?
Outside this case, yes, for hyperkähler, for Hilbert scheme of K3 surface, as long as you have such kind of multiplicative decomposition for Chow, you have.
Well, so that, is there like a prediction for exactly what kind of varieties have multiple?
So for the time being, the most natural guess is hyperkähler and Abelian varieties.
But is it like possible to see why the hyperkähler?
Not in principle, not philosophically, no. I don't know. It's just a guess. Maybe the second part of my talk will give some explanation of this. Yes, I expect that. But for example, product of our K3 surfaces. I mean, it's not irreducible holomorphic symplectic, but it's a holomorphic symplectic. I will expect that.
But you could see, like in a calculus, like a Hawkshaw circle.
Hawkshaw.
Spectral sequence that you get in a calculus homology from the calculus homology of the, say, finitely generated field, the number of fields, the algebraic proof, that one.
because the small diagonal will control the
Well,
multiplication.
that like all the raised function sequences that apply to x.
So the part 2 is that I will call it towards the strong multiplicative decomposition. The strong multiplicative splitting. Sorry. So if so in the second part, I think the language of motive is more natural here, more intrinsic. So I will denote by H the functor from the category of smooth projective varieties over C, opposite, contravariant functor, to the Chow motives with Q coefficients over the field of complex numbers. Then actually the strong splitting principle would imply that predict that for any Hyperkähler, projective Hyperkähler, we have a so-called Chow-Queenet decomposition, multiplicative Chow-Queenet decomposition. So HS decomposed into of dimension, say dimension 2n from I to 4n of HI of x, such that so x is the variety, so we have the diagonal map. Or viewed as a correspondence, this is just a small diagonal of x as a correspondence. So we have the multiplication map given by the small diagonal. When we look at the factor of hi, tensors hj, we would expect that it ends in it factors through hi plus j of x. Now I want to firstly speak of some recent result of Vial. So for x equal to the Hilbert scheme of K3 surfaces, then the theorem of Vial, it's printed in 2014, use some arguments of Beauville-Voisin, show that this is true for this. But let me remind you that we are additively, so this is true, so it's multiplicatively true here. So let me remind you that the theorem of Mark and Beauville-Voisin already gives an additive decomposition of this type. It's multiplicative. So if we look at the, yes, if we look at the correspondence given by the small diagonal, which is just the multiplication, then if we look at the hi and hj piece, it will give in the hi plus j piece, like in cohomology. And for the Decadado and Miolinis result for S a K3 surface, for example, then the motive of this Hilbert scheme decompose as I said, this is actually their original statement of the theorem that I stated. Mu, and the mu is just any, yeah. So yes. And if you look at this S mu, so this is theorem. If you look at S mu, is, as I said, is the product of symmetrical products of surfaces. And if you how to say, if you decompose every motive of surfaces by the standard decomposition given by mu 1 plus h2 of S plus 1 minus 2. Here 1 and 1 minus 2 is given by Beauville-Voisin class that I explained in the beginning. This is just CS times S. So motive is just a variety together with a projector. So here, this is just S times CS. And the H2 part of the motive is just S with diagonal minus these two classes. If you look at the decomposition here, and if we plug in this decomposition here, and we decompose by this Schroer-Functor thing, and we collect every term with the same degree, we get exactly the decomposition of Vial. And the conclusion of Vial's theorem says that this is actually multiplicative. But my point is that this gives a multiplicative. We know that the multiplication of hi times hj is in hi plus j, but we don't know the multiplication here. So the theorem that I recently worked out with Tian, Zhiyu Tian, is the following. So to state this theorem, let me remind you, first of all, some terminologies. So cohomologically, Ruan conjectured the following thing. So for any smooth projective variety, M, with an action of finite group, G, if we look at the quotient variety, which is singular, and if there exists some so-called crepant resolution, which says that the canonical bundle of this X is just the pullback of the canonical bundle of Mg, then assume X is hyperkähler, then we know the cohomology ring of X with Q coefficients, actually with C coefficient, but with change of signs, we can conjecture that Q coefficients is isomorphic as rings to the cohomology of the orbifold, the quotient stack of M over G. Now, here the example that is relevant to us is the case that M is the product of K3 surfaces, and the group G is just the symmetric group acting on this product. And this X, so the quotient is just a symmetric product, and the crepant resolution is just the Hilbert schema of K3 surfaces. And it says that the cohomology of this Hilbert schema of K3 surface as ring is isomorphic to the orbifold cohomology of this quotient stack. I apologize that I don't have time to explain what is the product of this orbifold cohomology, but let me tell you that the cohomology of the orbifold cohomology of this orbifold is just additively is just the cohomology of the so-called inertial stack of this guy, but with a very interesting product, so-called quantum product or orbifold product. Oh yes, no, if I put it that way, it's all right because a stack. So product. Okay. Now, the theorem that I want to say is that for S a K3 surface, we actually have the same result for Chow rings. So the Chow rings of Hilbert scheme with Q coefficient is isomorphic to the so-called orbifold Chow ring of this quotient stack. I should say that additively, this is exactly Mark and Degadado and Migliorini's result. So additively, the right-hand side is given by sigma of Sn some dimension shifting by the edge of this element of the fixed point of this action, and we take the invariant part. And this group acts on this fixed loci by conjugacy, and so this ends up with some. So it ends up with the direct sum over all the conjugacy classes of the symmetric group, which given by the partitions of n. So this is exactly S nu. Yeah. So it goes back to this result. But once we collect, as I explained here, once we collect all the pieces of the motives, so, oh, sorry, I should say that this actually is true for the Chow motives additively as so as algebraic objects in the category of Chow motives. As algebra objects. In Chow motives. Once we collect all the motivic pieces with same degree, we have this. We cover this theorem of Vial in that case. But I think in this formulation, we give a little bit more information about this morphism here. That's the point I want to say. I think my time is up. Thank you.
What kind of thing is involved in this proof or Vial's proof for that?
Oh, yeah. So, yes, actually, my proof is also along the same line of Vial's proof, which uses the argument of Voisin, says that if we have a cycle which is canonical in some sense or universally defined, stable by base change and the restriction, etc., then if it is cohomologically 0 for any surface, then it is 0 for K3 surface. So the point is that to control the product of X, so in some sense, this is equivalent to saying that we should have some control of the small diagonal of the X times X times X. So the goal is to understand the small diagonal of X times X times X. For X, the Hilbert scheme of K3 surfaces, of course. Then we use the result of Degadado and Migliorini to look at its image in the Chow of all products. I mean, L mu times L nu times L rho, for example. Then, because we can express the orbifold product by some cycles on the product of surfaces, and we only need to show that the image of this guy is something that we predicted. But how to prove these two cycles are the same? We first use that this is true for, in the cohomological class, which is proved by Zolger and Lan and Fadaki-Gocha. Now we need to say that if they are equal in cohomology, then they are equal in Chow. But this uses Claire's argument that this is something canonical, and we need to know that they are equal for every surface. I mean, for some very general surfaces. For that purpose, that argument of Claire is enough for Vial's theorem, because he just wants to prove some vanishing results here. So that's enough. But for our results, we need to know some cohomological relation which is universal for any surfaces other than K3 surfaces. Then we need to invoke this cohomological theorem of Qin, Li, and Wang, I think, saying that the quantum-corrected cohomology of the Hilbert scheme is isomorphic to the orbifold cohomology ring of the quotient stack. And then, because we know that the Gromov-Witten theory is no, it doesn't answer it. It's just a step towards it, but it doesn't answer it. It's analogous to the situation of Abelian varieties. By Beauville, we know the decomposition of the motive of Abelian varieties, or maybe due to Deininger and Muir, but we still don't know the conjecture of Beauville. Yeah, but I think this is just some step towards it.
Okay, thank you.